Hey guys, welcome to this podcast on the final SAC of the year. Hope you enjoyed, hope you find it useful. All right, let's begin with the multiple choice. There are the answers to the first 15 questions in case you wanted a quick snapshot. But let's start by looking at question one. So it's all about an object of mass 5 kilograms experiencing a constant force from rest. Constant, yeah? So you don't see any of those elements, any of those components in 3D being a function of time. So it's a constant force from rest. So you constant force, so you think constant acceleration. We need to determine the speed it reaches after 2 seconds. So again, F equals ma, dividing everything through by 5, and you've got an expression for acceleration. There it is. Okay, now it's constant acceleration, so we might as well analyze it using our constant acceleration formulas. What will be its speed after 2 seconds? V equals u plus at, u is equal to 0 because it's initially from a position of rest, and that's probably the easiest way to go about it. Of course, you could have used a vector calculus, determine a velocity vector function, subbed in t equals 2, subtract from t equals 0, etc. You would have got to the same endpoint. E was your final answer. Okay, question 2 should have been reasonably straightforward, I hope. So an object of mass is being pulled along a smooth horizontal surface by a 10 Newton force acting at 30 degrees to the horizontal. The diagram was given to you, so that certainly should have made it helpful. Okay, so we know it's being dragged along the surface, so forces perpendicular to the surface are in equilibrium. So your normal reaction force plus your resolved component of the 10 Newton force perpendicular to the plane will be perfectly counterbalanced by the weight force 2G, leading us to set up an equation for n to solve, and that also should have been relatively straightforward. All right, question 3 was all about a position vector function where the components were sine and cos with a common argument. So straight away, you should be thinking it's traveling in a circular or elliptical path. And in fact, because those multiples are not the same, it's an elliptical path. Very easy. That should have been a very quick and immediate way to determine the path, the Cartesian equation for the path in which it's traveling. So, but however, we not only needed to determine its path, we also needed to work out the direction in which it traveled. And a lot of students got this wrong. So let's just review what it takes to work out the direction. Firstly, work out where it's starting. So when t equals 0, you're left with the I component is -2, the j component is equal to 0. So we know it's starting down here, -2, 0 along the elliptical path. And this is my recommendation. It's quick to observe the period is equal to 4. 2 pi divided by pi on 2 is 4. Quarter of the period is 1. So where is the particle at t equals 1? Well, the I component this time is 0, and the j component is down here at -3. And so that's enough to give you the direction. So it's clearly traveling anti-clockwise, which is B. A lot of you actually had the wrong direction, but correct Cartesian equation. All right, question 4 was just a classic towing situation. A car of mass 1500 kg is towing a trailer of mass 600 kg via the usual light inextensible string along a rough horizontal surface. So when you're reading these questions, these are the words you highlight. So you know friction's at play. The car tows the trailer in a straight line and is accelerating with a magnitude of 0.5 meters per second. The second squared rather. Okay, so we know both of those objects are accelerating because it is a connected body situation with that magnitude. So because only tension is required in this question, we'll analyze everything around the trailer. So how does friction come into the situation? Well, it comes in at the next line of information. If the surface exerts a frictional force of 1/10 of the normal reaction force on both objects, the tension in the rope is. Okay, so as I said, we're going to analyze things in terms of the trailer. So there's 4 forces at play on the trailer. Tension force causing it to move in the direction of motion. You've got your weight force being perfectly counterbalanced by your normal reaction force because the trailer remains fixed to the road. So the normal reaction force is 600 G, and 1/10 of that is 60 G. So that's why you've got your frictional force opposing motion. It leads us to our F equals ma equation. So the resultant force is tension minus 60 G equals mass of the trailer, 600 times by 1/2. And obviously we resolve that equation for T and we get our answer. Now you could have, of course, analysed it in terms of the car. Oops, actually I'll get a different colour. In terms of the car, so the car would have some sort of pulling force, and then you've got your tension force opposing that pulling force. So the same in magnitude as the tension force in the rope from the perspective of the trailer, causing it in the direction of motion. And of course, the frictional force will be 1/20 of 1500 G, which is 150 G. But of course, then it involves an extra element of pulling force, and we're not interested in pulling force, only in the tension in the rope. So it's certainly easier to analyze things just in terms of the trailer. Okay, question 5 is just a kinematics question. How do I know that? Is your dead giveaway. It's a particle moving in a straight line. Okay, you're given an equation. This equation is linking velocity and displacement, v and x. Okay, v is measured in meters per second, x in meters. X is, of course, the position relative to an origin. The particle is starting at e minus 1, so roughly 2.7 minus 1 at 1.7, the right of the origin. If we think right, positive, and left, negative now. Okay, what do we need to find? We need to find a relationship between x and t. So we need to transition from this relationship between v and x to a relationship between x and t. So it sparks the connection. What is velocity? Velocity is the rate of change of position with respect to time, or displacement with respect to time. And there it is. So once we've made that connection, it's all about going through the process. I've actually done this by hand, but of course you've got your DE solve to work with. But of course, it's a fairly easy process by hand. We reciprocate. First line, we anti-derive with respect to t. Okay, so then we've got it's a fairly straightforward anti-diff process. We sub in our initial conditions when t equals 0, x is equal to e minus 1, log of 1 is 0, therefore c is equal to 0. So from here, you've really got the understanding that t is equal to minus natural log e, let's just get rid of that. Back to my x, so e minus x. So we go make mod of e minus x subject. You've got e to the minus t, and then of course you've got your two options. You've got your plus or your minus of e to the minus t. Which is the correct one? Well, I know when t equals 0, x is equal to e minus 1. The only thing that satisfies that would be, of course, the positive version. So in fact, therefore, which leads to, just bring up this one, leads to that version is the one we're going to run with. So we're going to reject the negative in that particular case. And then, of course, it easily transposes to option E. So hopefully that's fairly well understood. Okay, so question 6 was an equilibrium question involving 3 forces. So we've talked about several different ways you can unpack and solve questions where there's 3 forces in equilibrium. As you can see here, I've gone with Lami's theorem, but there's a couple of other equally valid ones that you could have used. But let's have a look at this situation. So we've got a 4 kg mass that hangs freely from the ceiling via a light inextensible string, experiences a horizontal force F that pushes it until the string is angled at 30 degrees. So there it is. It's naturally going to be wanting to dangle directly below, but it's pushed to the right, and that's the resultant situation. So the first thing I would do is just put it into its classic force diagram that you can see over here. Horizontal force F, you've got your weight force, and then of course you've got your tension in the string force. So there's your three forces at play. All right. Now, if you weren't aware that there were three forces here, please brush up on your mechanics and your equilibrium work. Okay, 30 degrees lies up here. So let me just change the color here. There's 30 degrees in here, therefore 30 degrees with the vertical. Easy to work out the angle between T and F is 120 degrees. 60 degrees belongs here. 90 degrees between the horizontal and our weight force, making it 150 in there. Pretty easy to analyze all of that. Now I've gone with Lami's theorem because provided it's the magnitude of the force I need to work out, and there are three forces at play in equilibrium, it's just the neatest way to go about things. So F relates to sine of the angle opposite, 150, as 4G relates to what sine of the angle opposite is, and then of course we can get a solution for F. F is 4G on root 3, which rationalized gives us answer A. All right, now of course, being right angles, you could have easily created a triangle of forces, so it could have been 4G, you've got your F, and then, the angle between F and T, there is, so it must be 60 degrees in here, and you could have gone about it just straightforward with our tan, as it turns out. So tan of 60, which is root 3, which is equal to F, and in fact, dividing through by root 3, multiplying by F gives us exactly the same answers we've had above. So that would also be an equally nice way to go about it. Or IJ resolution of forces would be a third approach, but of course, when you've got 90 degrees perpendicular between two forces, one of these two approaches is probably preferable. Okay, good, let's move on. All right, question 7 is another kinematics. How do we know kinematics? Because we're talking about a particle moving in a straight line relative to an origin. It starts 4 centimeters to the right and moves left with its velocity described by that rule. So hence you can see it's always negative for all values of x. V is negative, so it's constantly moving towards the left. Okay, and of course it starts at x equals 4, and as x gets less than 4, you can see it's still always going to be positive inside the square root. So it's all nice and good. The acceleration of the particle at the origin. So we need a relationship between A and x. Okay, the acceleration of the particle at the origin. Find that relationship between A and x. We're given a relationship between B and x. How do we develop that relationship between A and x? So those of you on the ball would have realized that version of acceleration is the one to appeal to in this particular question. So of course you could have gone A is V dv dx and use separation of variables, but you're way overcomplicating the matter. So what we need to do is just take our expression for V, square it, and halve it. And that turns out to be a very easy rule as a result. The derivative of that with respect to x gives us our acceleration. And so you can see there's constant acceleration. An acceleration of 1 meters per second squared to the left is what that's indicating. So not only will it have an acceleration of -1 at the origin, it'll have an acceleration of -1 anywhere on its journey as it starts 4 to the right and moves to the left. All right, question 8 was the last of our equilibrium problems. There are 3 equilibrium problems that we've encountered in the multiple choice. A 2 kilo mass is held suspended in the air by 2 strings attached to a ceiling. Okay. The magnitudes of the tension in the 2 strings are, as you can see, at 10 newtons and 14 units. In fact, there was a diagram given. So in fact, it is a situation of equilibrium. It's a static situation, and you're given 3 forces. You need to work out the angle theta between 2 of those forces. Okay, So those of you on the ball would have realized that the only way when given all three forces in a situation of equilibrium involving three forces, and you have to work out the angle between any two, it's all about the cosine rule. So first things first, we take our force diagram that you can see on the left, and I've created a closed triangle force on the right. So there's our weight force, and then there's our 14 Newton force, and then there's our 10 Newton force. Okay, now recall the angle theta is the angle between the 10 Newton force, but in the closed triangle that becomes 180 minus theta. Okay, and then it's all about using the cosine rule. Here's your B and C. As you apply the rule for the magnitudes of the lengths on either side of the required angle, and this is your A in application rule, and there it is. So you apply the rule as follows: 180 minus theta turns out to be 108 degrees, therefore the required angle was 70 degrees. So decided to just change the order of our responses, that's all. So 72 degrees was the answer there. Okay, so question 9 is again kinematics. Okay, it's the story of an object thrown directly upwards, so motion in a straight line. Initial speed of u. Okay, so you might be thinking of constant acceleration, but hands off, because there's air resistance equal to kv squared newtons. Okay, so on its way up, where up is positive, it's going to experience its gravity force of g meters per second squared, or no, m times g meters per m times g newtons going downwards. But of course, because it's also going up, it's going to be experiencing that kv squared and that mg. There is forces opposing its motion, which is positive up. There's no force causing it, continuing to cause it to move upwards. It's all about that initial speed that got the process running. So I can express it as an F equals ma as follows. Ma is equal to our two opposing resistive forces. One, of course, is all about gravity, and the other one is all about air resistance. So they're both opposing motion, motion being positive in the upwards direction, and there we have it. Dividing through by m, we get this nice little expression. But we need to go back to the question itself. So let's just go back, and what do we need? What's required by the question? It's all about a link between time. Let me just grab the time it takes to reach maximum height. So we need to find a link between t. That's a terrible word to use. A link between t and x. So what have we got? We've got my bad. Not between t and x. Maximum height, of course, occurs in v equals 0. So we need to find that link between t and v. That's our link. Our link between t and v, and we're talking about the height gained when the velocity changes from u to 0. Okay, so that's what it's all about. So we need to find t when v equals 0. In other words, here it is. We'll resume our discussion. So this is how you decide which version of acceleration to use. So here's our expression for acceleration. It's not about v dv dx. We're not linking velocity and position. We're not linking acceleration and position. We're linking velocity and time. So we replace acceleration with a dv dt expression. Once you've made that link, it's straightforward. We need to reciprocate. I've just factored out the m. Here's our initial velocity. So when t equals 0, v is equal to u, and we need to find a time v equals to 0, the time it took to reach maximum height. So it's set up nicely by that definite integral. Of course, there is no, you'd normally go plus the time at which v is equal to u, but of course that's occurring at initial velocity. And then there was a little bit of a trick, if you like. So let's just look at this expression here. That's what I've just worked out as meeting the information given and the information required, and then you're just looking for the form that you see to the left, and you don't see that form exactly, but all I've done is just change it from minus m to positive m, and just change the direction of the terminals from u to 0 to 0 to u, and therefore it's the same form, but just in a different guise. So hopefully that all made sense to you. All right, here we've got three forces at play on a particle, but it's not a situation of equilibrium. Okay, we've got three forces, 2 newtons, 5 newtons, and 3 newtons. Theta is the angle between the 3 newton and 5 newton force. 90 degrees the angle between the 2 newton and 5 newton force. If the resultant force is in the direction of the 5 newton force, then theta must be. Okay, now the best way, this is actually quite a simple problem to solve. The best way would be to analyze it via resolution of forces. So let's just set up our x and our y. So I in the direction of positive x, j in the direction of positive y. And so when all three forces are resolved, there is 0 I component. So this 2 newton force in the positive I direction must be balanced by the 3 newton force when resolved in the x direction. It must have equal and opposite magnitude. So that's why it just comes down to this. Whatever the angle between the x-axis and the 3 newton force, let's just call it alpha. We can find alpha quickly enough, understanding that this magnitude must be equal but opposite to the 2 newton force in the positive x direction. So it must have a magnitude of 2 newtons. 2 newtons. So we can set up that triangle, work out the angle. Inverse cos, as it turns out to be, of 2/3 is 48 degrees. That's the angle made between 3 newton force and the x-axis, but of course it's in the negative direction. The total angle between the 5 newton force and the 3 newton force, therefore, is 90 plus that alpha, which turns out to be 138 degrees. So nice question and quite a clean, simple solution. All right, I guess this was a bit of a mean one to put as a multiple choice because there was a fair bit of thinking and understanding involved in all of this, but it's actually not too bad when you think about it, and it had a purpose in being there on the paper. So what are we talking about here? A 10 kg mass is held in a fixed position on a plane, 45 degrees, and then it is released. On its downward journey, it experiences total resistance equal to v squared on 10 newtons. Okay, so here it is. F equals ma. Well, actually, let me just reverse that. So ma equals resultant force. Let's just write it as R. Now, of course, our 10 kilograms has a 10 g weight force when resolved in the direction down the plane. So 10 g times by sine 45 turns out to be 5 root 2g. So that's the force due to gravity when resolved down the plane. Here is the resistive force. So it's not one of those proportional to the normal reaction force that you're so used to with constant acceleration. It's in fact variable acceleration. All right, from there, once you've made this leap, that's probably the biggest step, dividing through by 10, creating a singular fraction, which you'll always need to do, because of course, often it involves reciprocating. But let's go back to the question. What do we need to find again? Okay, what we need to find is, in fact, the distance travel down the plane before it reaches a speed of 20 meters per second. Remember, it's being released from rest before being released. So it's in a position of rest. It goes from an initial speed of 0 to a speed of 20. How far does it travel down the plane before it reaches that speed? So what do we need a link between? We need a link between v and x. There's our linking terms. So we understand our acceleration. We need that link between v and x. So it's not a case of half v squared dx, although we can in fact do it. Those of you can actually do it that way, but I'm not going to go talk about that here. But it's not about expressing acceleration as dv dt, a relationship between velocity and time, as we did in our previous question. It's understanding the relationship between v and x, therefore v dv dx is the way to go. All right, dividing through by v and then reciprocating. Okay, so there's our dv dx expression. So we need to reciprocate. Therefore, dx on dv is equal to 100v over d root 2g minus v squared. And of course, it starts x equals 0 when v equals 0. We need to find x when v is equal to 20. And so it's just finding those terminals. You can see in all options, the terminals 0 to 20. It was really about getting to this point, and reciprocating was the key. All right, so we finish with a string of statistics questions, four statistics questions to finish it off. SAC scores were calculated independently and were normally distributed. Okay, both of which are true. The mean SPECH score for SAC1 was 60%, standard deviation of 17%. Okay, also true. The mean SPECH score for SAC2 was 63, with a smaller standard deviation. In fact, I accentuated the standard deviation a little bit. I mean, made it less than what it was, just to have a point of difference. But there you go, it's pretty accurate. Okay, what we're looking at is this idea of current percentage score of a SPECH student. And a current percentage score is made up of 2/3 of SAC1 plus 1/3 of SAC2. Find the probability that this current percentage score, we're going to call it X, will be greater than 70%. Okay, so that's what we're after. We're after a higher order random variable that's a combination, a linear combination of two other random variables, S1 and S2, both of whom are normal. Therefore, X is also normal. So it can be, the answer can be determined via your norm CDF. All right, so here's our key data. SAC1, 60, standard deviation of 17. SAC2, 63, standard deviation of 13. We can easily work out our expected value of X. Turns out to be 61, 2/3 of one, 1/3 of the other. Okay, we need to work out our standard deviation of X, and we do so via the variance. So, and of course, we just take the square of our standard deviations in order to make that determination. But of course, what happens when you calculate the variance? It's the multiple of each of those random variables squared. So 2/3 squared plus 1/3 squared, and take the square of the standard deviations, take the square root of that sum, and you get the standard deviation of X. Okay, we know the standard deviation of X, we know the expected value of X, and therefore we whack it into our norm CDF, minimum of 70, maximum positive infinity, so on and so forth. It turns out to be C as your answer. All right, question 13. A farmer in northwestern Victoria grows Valencia oranges. He sorts his oranges into large, medium, and small. His large oranges are normally distributed. Okay. Mean weight, 170 grams. Standard deviation of 5 grams. Okay. Now the farmer sells these large oranges in bags of 6, and he tells the general public that they're buying 1 kilo of oranges. what percentage of bags will be underweight, under the advertised weight of 1 kilogram? Or, of course, because we're dealing with grams, they call it under 1,000 grams. All right, this is a case of course, I needed to test this in your SAC, a case of not 6 times one member drawn from X, X being the random variable for the weight of a single orange, but rather 6 members from the identical distribution. So it's not a case of 6 times X, it's a case of X1 plus X2 plus X3 up to X6, so 6 members from X. With that understanding, you get important differences in your answers. So the expected weight of our 6 oranges is in fact 6 times our expected value of 1, which turns out to be 1,020 grams. But the calculation of the variance is in fact 6 times the variance of X, so which is 6 times 5 squared, because we're told that the standard deviation was 5 grams, which is 150 grams. We take the square root and we get the standard deviation of in grams of bags of oranges of 6. So find the probability that this y variable will be less than 1,000. It's all about our norm CDF using expected value 1,020, standard deviation of 5 root 6. Turns out to be 5.1%. All right, the last 2 questions were more about those chapter 16 hypothesis testing questions. So we're testing hypotheses. Mu is 30 is our null hypothesis, and our alternate hypothesis is mu is simply not 30. Okay, all right, so straight away, not equals, you're thinking a two-tailed test. Okay, so what we're going to do is collect 25 members from the variable and work out our sample mean. Our sample mean turns out to be 29.1. Okay, so if sigma is of our random variable x is 2.5, then it is not true that the p-value, it is not true that the p-value is. Okay, so the p-value always refers to a specific sample estimate. In this case, our sample estimate is 29.2, and our p-value concerns a two-tailed test. All right, p-value, two-tailed test. So I've drawn a little diagram here. Here's our actual sample estimate. Okay, now here is a value that's equally distant from the mean. So 29.1 has a distance of 0.9 from the mean. So on the other side, at the upper tail, at the right tail, that would be mark a boundary of 30.9. So the p-value is in fact the probability that some other sample estimate with a sample size of 25 has a sample mean less than 29.1, so at the lower end of the tail, or greater than 30.9. So those two regions in the sampling distribution X bar is what we're looking at. Okay, with all that in mind, we can go through our options here. So clearly, so you see those in for A, you've got those mods. So we're talking about distance that the sample mean will be from 30 is greater than 0.9. Clearly it covers anything less than 29.1, less than or equal to, or greater than 30.9. So that's a perfectly reasonable way to describe the calculation of a p-value in this two-tailed test environment. Of course, so is the second one, because of the symmetry of the normal curve, the area below 29.1, we can just double it. Now this one, to understand how it relates to the standard normal distribution, we need to appreciate, well, is that right? What is 29.1 as a z-score, as number of standard deviations above or below the mean? And the formula is quite simple. So the actual score here minus the mean divided by the standard deviation. And in fact, that represents a standard score of minus 8.1. So of course, to say that the probability that the modulus of Z is greater than 1.8 is to say that, so in terms of a Z score, this of course, this 0.9 is equivalent to 1.8 at the Z score. So they're saying that it's the distance, the probability of our member from the our sample mean having a Z score greater than 1.8 covers exactly the same understanding. So, okay, Z score, of course. Okay, so and the mod. Now, clearly that means D is incorrect. So that's really, in fact, let me just draw Z score. Our ended. So we're talking about here is 0, -1, +1. We're talking about area below -1.8 and above +1. They're the two areas of our standard normal curve that represents the p-value in this particular case. Now, that's clearly not going to be correct because what we're talking about is calculating 0.9 to -0.9 to positive. We're talking about that area. Clearly, it's not going to be this. It's going to be a much larger probability value than less than -1.8 times 2, or as a distance of 1.8 from the center of 0, greater than that. So clearly this is not correct. Okay. Now you can, in order to show that E is in fact true, you'd need to actually go and calculate the p-value, and then you can see, in fact, the p-value would be greater than 5%, which, in fact, you'd only bother to do if you had time, if you finished the SAC early, which I doubt many of you did. But once you come up with what you're pretty sure is the incorrect answer, mark it as your answer, move on, and just put a little asterisk, go and check the other options to ensure that, just to verify that that is indeed the answer to give in this case, the one that is not equal to the p-value. So, but of course, yeah, you could just run it through your calculator and appreciate that the p-value was greater than 5%, as E was suggesting. Okay, hopefully that's clear enough. Okay, welcome to the final multiple choice question in the paper. Okay, so we've got fully charged solar panels being manufactured by company X, and we're told that they have a mean energy output of 275 watts with a standard deviation of 5 watts. Okay, now company X are making a claim. Their claim is that their latest model of solar panel offers an improvement in the amount of energy it can produce. An improvement. All right. Now, this claim is going to be tested. So what we're going to be doing is essentially working with these hypotheses. We're going to start with the conservative claim that, in fact, these new solar panels are no different from their old ones. So the mean still is 275. And our alternate hypothesis is, in fact, that things have improved, that, in fact, no, they are different. And we can actually say, verify their claim that the mean energy output has improved, is greater than 275. So what do? Now, the independent testers take 20 of these. So n is equal to 20. Okay, and they generate a sample mean. Now, their alpha, their level of statistical significance, is not the usual 5%, it's only 2%. All right, so what would be the least value of X bar for the independent testers to accept the claim made by company X? Now, the least integer value for the independent testers to make the claim by company X. All right, so this is one of those cases where we have to work backwards. So we're going to start with the specifics of our normal distribution, and what we're going to do is work out what would the value need to be for the top end to be 2%? So what part of our calculator do we use? We use our inverse norm. So inverse norm is where we know the percentage value. We want to work out backwards to a member of the distribution for which greater than that or less than that is, or whatever the case may be, gives you the right value. So there we go, inverse norm. We're looking to the right tail, 2%. Of course, the standard deviation of our original x divided by the square root of the sample size, which is 20, and there's our median, our mean value in the null hypothesis of 275, and it turns out to be 277.3. So a value greater than 277.3 would make our independent testers accept the claim. Now, of course, you see 277 there, but it's the least integer value for them to accept the claim. If you got a 277 claim, it's not quite great enough, but 278 is the least integer value for them to accept the claim. And so it's not A, but it's in fact B is the one you needed to go for. So X bar for them to accept the claim, to accept the confident hypothesis, had to be greater than 273. But the least integer value for which for that occurs is 278, 277. So that's how you have to go through that one. All right, from the multiple choice, we move into the extended response. That's where the money lies, guys. So, okay, 2 motorized boats, we're told, A and B, travel from 12 noon to 4 p.m., so 4-hour journey, according to the following position vector function. There's boat A and boat B. Okay, now it's relative to a point on a dock nearby, marking the origin. T is time in hours, and the positive I direction is kilometers east, positive J direction, kilometers north. Okay, very nice. So they're like compass directions, if you like. Show that these boats do not collide. Okay, if they did collide, they'd be at the same I location and J location for a common time. Okay, so all right, so hopefully, I think most of you did this reasonably well, in fact. So let's just have a look. So we start with the same X location as determined by our I. So of course, it's all about just setting the two I equations equal to one another, solving P. Okay, so after 1.5 hours, they're at the same east-west location. Okay, now of course, if they're at the same Y location, north-south location at T equals 1.5, then they have indeed collided. So what we can do, the easiest way to go about it is to just sub T equals 3 on 2 into the boat A expression. And of course, after 1.5 hours, it's at 3J, indicating 3 kilometers north. For boat B, it's we substitute 1.5 hours into it, and we get 3/4 of J, so 750 meters north. So they're clearly not at the same location, and so that's enough evidence to supply to show that they do not collide. They're not at the same XY location at the same time. That's what it's all about. Now, others of you did it in different ways. If you just have a look at your papers, if you got full marks for it, of course, if you solved both equations, you could have, some of you actually solved the first equation, solved the second equation, so set 6 minus 2t equals to t squared minus t, solved for t, took the positive value, showed that that was not the same as 3 on 2. That was also a perfectly valid way to go about it. Okay, from there we progress to find the Cartesian. Let me just get rid of that. Find the Cartesian expression. The Cartesian expression for the path made by boat A and the path made by boat B. All right, so most of you are pretty good at this. You just set X, you align X with your I component. So that becomes your X. And let me just grab a different color. You align your J components with Y. And then you remove the T expressions. In this case, just let T equals let t in, describe t in terms of x, and then substitute that t expression for x in terms of your y, and that's the easiest way to go about it. Let's see how we've done it over here. So for boat A, very, very simple, transposing that equation involving x in terms of an equation where t is the subject, and replacing wherever I see t in the rule for y, replacing it with that x expression. I get a nice simple, you can see it's traveling along a straight line path there. Now for boat B, I do the same process exactly. I've got to make t the subject, which is a little bit more awkward. It's going to be 2 minus x divided by 3. And you can see t occurs twice in the expression for y, one squared, one not. And in fact, giving an answer in that in that basic form was enough to get your second mark. But of course, unless you simplified it, it was very hard. You would know how to sketch it. But of course I gave 1 mark for this and 1 mark for boat B. And of course you could have even taken that rule and just go simplify with your CAS, and it would have come up with that neater expression that you can see down below. That's an easy parabola to draw. Okay, part C was just a simple sketch. I was a bit disappointed a lot more of you didn't get full marks for this. Sketch these paths on the axes below for t equals 0 to 4, marking the 4-hour journey by both boats, marking endpoints, taking note of everything you need to point of intersection, and the direction of travel. A lot of you forgot to mark the direction. Okay, for boat A, it was a straight line function. I think it was y equals minus 2x minus 2. Now, of course, it's not the whole, so that's this straight line graph that you see below, but of course it starts at t equals 0 and it moves to t equals 4, and so you've got clear endpoints. So a lot of you are just sketching the whole line graphs, but of course understand where it starts and where it ends, and therefore the direction of travel. So that really should have been a straightforward pair of marks to pick up. Now the second one, as we saw, was a parabola, boat B, traveling along a parabolic path, but it's not the whole parabola, people. It's in fact starts when t is equal to 0, looking at your x and y rule. You're actually starting here at t equals 0, and at t equals 4, you're ending here at minus 10, 12. Okay, now in this parabola, of course, it starts on the x-axis at 2, 0, and it's easy enough to show it crosses the x-axis at minus 1, and that just turned out to be a convenient point because it was also the point of intersection, so it was a common point between the two paths. So this is a case where the two boats, their paths are crossing, but they're clearly not colliding, as we established in part A. So a lot of you went and overanalyzed part A to work out where they're crossing but not colliding. There was no need to do that in this question. It was simply a case of the point of intersection just being immediately given to you once you sketch the key points on both paths. Okay, so hopefully that should be clear enough. The direction of travel needed to be indicated. I've got a few arrowheads along each path. Only one arrowhead would be sufficient, but that's the sort of thing you need to do to pick up your full marks. And here's the marking scheme I gave. So two marks for the endpoints, 1 for the point of intersection, which was easy enough to establish, half a mark each for the direction. And I just thought if your parabolas didn't look like a parabola, or your straight line didn't look like a straight line, then you'd actually lose a mark as well for that. Hopefully that was pretty clear. That was designed to be fairly easy marks, but it was quite amazing how many people didn't find that easy at all. Okay. All right, the next part of the question was find the time of day when the boats A and B are closest. Now, I just added to correct to the nearest minute. Now, the first thing to realize in these vector questions or vector function questions Simply the position vector function to one minus the position vector function to the other gives us the vector connecting the two boats for any given time t, and if I take the magnitude of that, then I've got the distance. So please take note carefully when you're talking about the distance between two objects that are whose paths are determined by position vector functions. This is the way to do it. It's just the magnitude of the position vector function to one minus the position vector function to the other, give us the magnitude of the vector connecting the two objects at any time t. That's all about the distance. So once you've got appreciated that, working the time of day when they are closest becomes a simple matter. So we want to minimize distance. Find the value of t when our distance is at a minimum. And what's that all about? That's all about our calculus. So there's our rule for the distance. So our I components subtracted from each other squared plus our j components subtracted from each other squared, square root, of course. That's all about taking the magnitude of a vector. That's what we do. So the magnitude of AI, BJ, of course, it's just that's all I'm doing in coming up with that particular expression. Now, of course, here it is, differentiating, setting it to 0, and it turns out it's equal to 0 when t hits this particular value. When it's 1.789 hours after midday, so I just take that that fraction of a whole, times it by 60, and I can easily convert that to time. So hour hits 1.47 p.m. They're at their closest point. It doesn't ask us how far that distance is. It's just simply the time of day when they are closest. So that's satisfactory for your 3 marks. Okay, moving on. E was easy. Hopefully everyone got this. I think most people did. Find the velocity of boat A and the velocity of boat B as a function of t. So obviously you just have to differentiate their I and j components individually, and you mark them as r dot A function of B, r dot B function of B. Okay, F. Show that boat B is always traveling faster. Traveling faster. What is that all about? Has greater speed. So the first thing to recognize is you need to pull up an expression for the speed of boat A and boat B. So boat A was traveling with a constant speed. So just take your r dot A, your I component squared, your j component squared, square root. It turns out to be a constant speed of root 5. Your boat B is traveling, there's the expression. So the I component was constant, but the j component was not. And I come up with a rule for its speed. It's equal to that, the square root of 9 plus 2t minus 1 all squared gives us the speed of boat B. So to show that boat B is always traveling faster than boat A, so show us that the square root of 9 plus 2t minus 1 squared is always greater than the square root of 5. I can drop the square roots because, of course, that square root is an increasing function. And it's enough to state that 5 will always be less than 9 plus 2t minus 1 squared, because regardless of what t is, any value of t from 0 onwards, what would have been nice, of course, would be 5 is strictly less than 9, which is less than or equal to 9 plus 2t for all t. The only time the expression 9 plus 2t minus 1 squared is equal to 9 is, of course, when t equals 1/2, but for all other values of t, it's going to be greater than 9, which is clearly greater than 5, and that's enough to establish that B is indeed traveling faster. All right, the last part of this section was just testing your understanding of average speed. Average speed is total distance divided by total time, average speed in kilometers per hour for the 4-hour journey. So there it is, there's your arc length formula. So we're integrating from t equals 0 to t equals 4 divided by the total time, which is 4 hours. And of course, it's your component for r dot squared. This is for boat B, by the way. And there's your component for R dot in the J direction. We square them, we take the square root, you run it through your calculator. It turns out to be 4.6 kilometers per hour, 4.60 correct, 2 decimal places. All right, hopefully that's all good. So that was question 1. It was done okay, let's say. Okay, question 2 was your classic connected bodies problem. I had to throw in one. We practiced several like this in class, not exactly like this, but with a similar kind of structure and thinking behind it. So it was therefore a little disappointing it wasn't done a little better than this, because it was the sort of question that should have been familiar to you. So let's just go through it. We've got two masses of 5 kg, and that should have been 15. That's the diagram. 15 kg are released from rest on a back-to-back inclined plane. The angle of inclination and on the surfaces, the angle of inclination and surfaces on both sides are the same. The bodies are connected by a light inextensible string over a smooth pulley, standard stuff. The tangent of the angle of inclination, theta, is 3/4. So there, and I've just made it nice and clear for you on the diagram, I would have thought. There's your constant angle of inclination on both sides of the back-to-back inclined plane, and there's tan of theta is equal to 3/4. Okay, when you see it in that form, I think most of you did this. I actually gave you 1 mark for the next part. You automatically think, because you've got to resolve your weight forces parallel and perpendicular to the plane, it gives rise to very clean, nice expressions for sine of theta and cos of theta. No need to work out theta via your calculator at all in these instances. So please remember that, those of you who didn't. Okay, so the tangent of the angle is 3/4, and each body experiences friction equal in size to 1/4 of its normal reaction force. Okay, there it is. So the first part was draw and label. Draw and label all forces on the diagram above. So you can see, actually this was done really quite well. A lot of you are using those subscripts. So there's the friction force going up the plane for the 15, because of course, firstly, we need to appreciate that this system, once it's released, is moving to the right. Now, obviously, the 15 kilogram mass is driving it. So the friction force opposes motion. So it's F1 and N1. Tension force, we don't give it a different subscript because it's the same magnitude. Tension force pulling up the plane, the 5 kilo, and tension force resisting its natural motion down to the right for the 15 kilo force. Okay, but then of course you need N2 and F2 to match those forces. I actually, just for weight forces, I just actually write MA, or M times G. And these are all the forces at play. So there's each force, each body has a weight force, has a normal reaction force. So has a weight force, has a normal reaction force, has a friction force opposing the direction of motion, which is to the right. And of course, there's the tension forces that need to be labeled as well. So that's it. It was done quite well over, I'd have to say. All right, B, show the system is accelerating with a magnitude of g on 10 meters per second squared. Okay, I've done it body by body. Some of you competent ones out there, or those comfortable with this, just analyze it as a system as a whole, and that's perfectly okay. So either way, I didn't mind. This is how it's done body by body. So F equals ma, let's analyze all the forces around the 15 kg object. So of course, here's our weight force resolved down the plane in the direction of motion, and it's opposed by its 1/4 of the normal reaction force. The normal reaction force is of course 15g cos theta minus the tension. So then we replace sine theta with 3/5, cos theta with 4/5, and it turns out to be a nice, neat little equation here. So 15a equals 6g minus t. So I was looking for that kind of methodology. When we look at all the forces around the 5 kg object, the tension is the force pulling it up the plane. here's the weight force resolved down the plane, and here's the 1/4 of the normal reaction force, which ends up being the friction force. Replace sine theta with 3/5, cos theta with 4/5, and we're left with T minus 4G. I put the two together. So equation 1 plus equation 2, sum them together, of course the tension drops out, but when you're analysing it as a whole, there's no need to introduce tension, so it is slightly more efficient, but I just want you to get these done accurately, so do whatever feels comfortable for you. The tension drops out, you're left with 6G minus 4G, which is 2G, and therefore leading to the correct answer. All right, this next part should have been familiar to you. We must have practiced this about 3 times in class in various guises. So after 5 seconds, the string connecting the two bodies is cut. You may assume that the loose string does not affect the movement of either body thereafter. Okay, determine how many meters the 5 kg bodies continues up the plane after the string is cut. So first things first, draw yourself a nice diagram of what's happening in this revised situation. So there's its weight force. Of course, I don't have the normal reaction force. If it was going to be a full force diagram, it'd be working perpendicular to the plane, but there is no force causing it up the plane, just the two forces. So here's our weight force resolved down the plane, and our frictional force, which is 1/4 of the normal reaction force, which would be equal to 4G. They're the two forces resisting motion, no forces in the direction of motion. That leads you to this setup. So F equals MA. So MA 5 times A is equal to 0 forces in the positive direction of motion, minus 3G minus G. So here's your weight force resolved down the plane, your frictional force, and it leads you to an expression for acceleration. In this case, it's a deceleration because it's negative and we've made positive the direction of motion. All right, from there, what do we do? Now, in order to work out how far it travels up, we need to link it in with what was happening at the moment the string was cut. And what we're really after is the speed it obtains after those 5 seconds at the moment of the string that was cut. So, of course, the system starts at rest and is released. So the previous acceleration of the system was g on 5. It's in operation for 5 seconds. So it's actually reached a speed of g on 2 or 4.9 meters per second. Okay, so I was looking for those two answers in your working out. All right, so I know that the deceleration value, I know the initial speed value. I should be able to work out distance traveled, so which of our constant acceleration formulas, and it is of course a situational constant acceleration. I've got to appeal to b squared equals u squared plus 2as. Why? Because I know our final velocity is 0, our initial velocity is g on 2. I know the acceleration is minus 4g on 5, and from there I can work out, I know 3 of the 4 variables, so I can work out s. Transpose to make s the subject, sub it in, and I get 49 on 32, or 1.53125. If you've rounded it off sooner than that, of course I had to take off a mark, or maybe half a mark, I don't know how generous I was, but always nice to leave it in it as a fraction if it's something neat like that. Okay, the final part of this question, determine the speed that it obtains when it returns to the original position, or the position at the point where the string was cut. First things first, just quickly redraw your diagram. Now, of course, frictional force this time, 1/4 of the normal reaction force, is now going up the plane because it's opposing motion. What I've decided to do, I always like to make the direction of motion positive. So I've made direction of motion down the plane this time. So G is going up the plane, and of course, with the direction of motion, we've got our weight force resolved down the plane. Okay, so of course I need to recalculate our acceleration in the direction of motion. MA equals our weight force minus our friction force. Acceleration is 2g on 5. Okay, so therefore I can work out our final, our speed, our velocity, so initial speed because it's starting at rest, equals 2 times acceleration, which we just calculated, and the distance that it travels is our answer to our previous question. I gave consequential marks in this particular case. Whack it all together, it turns out to be 3.46 meters per second. So it was speed rather than velocity, so all good there. All right, guys, let's have a look at question 3. I quite like question 3. I think it was a nice addition. It was a nice link between kinematics and dynamics. All right, so what are we dealing with here? We're dealing with a ball, spherical ball, as it turns out, of mass 150 grams. So there it is. So 0.15 kg. Okay, it's attached at the end of a light, inextensible string, fitted via a fitted cap of negligible mass. So that's the situation. So in this situation, it's traveling up and down, not left and right. There's no swinging involved. It's just pure up and down. And we're told that upwards is positive and downwards motion is negative. Okay, we're told that further on in the question over here. Positive velocity marks upwards motion. The ball is moved up and down via the string attached to the fitted cap according to the velocity time graph. All right, now when you're in your reading time, you should be able to look at a graph like that. And here's an important part as well. The ball initially starts at ground level. So when t equals 0, it's actually at ground level. And therefore the graph starts to make sense. So you can see it starts with an initial speed of 4 meters per second in the upwards direction. So this is all upwards. This is upwards travel. When its velocity is momentarily at rest, it's at the top of its journey, and then this down here indicates downwards motion. Okay. It then slows, it then is initially at rest, and then it returns to travel in the upwards direction. All right, so when you're just looking at information at reading time, slow the heart rate, just really just understand what sort of information you're given and start to think about what this means in the given context, okay? So it's just moving up and down along this string. It has a particular mass, and that's the journey is neatly captured by that velocity time graph. Okay, let's begin. Okay, show that the ball is momentarily at rest after 3 seconds. Okay, so you can see the graph is linear between t equals 0 and t equals 4.5. Okay, and we're given the initial speed or initial velocity and its final velocity of 2 to the left, or 2 downwards rather, 2 meters per second downwards after 4.5 seconds. But what we've got is constant a constant acceleration throughout that journey. Okay, so so what we need to do is the best way to work out when it's momentarily at rest, the value of v when t, the value of t when v is equal to 0, is to come up with a rule for that straight line. So clearly it's just a straight line, therefore it's of the form y equals mx plus c. The gradient difference between our y values over difference between our x values gives us minus 4 on 3. And of course we've got immediate access to c, the y-intercept, in this case the v-intercept. So straight away, without any further calculation, we get our rule for v. v is 4 minus 4 on 3 times t. Setting v equals to 0, solving for t, it's easy to establish that the ball is momentarily at rest at t equals 3. So the value of t for that intercept is equal to 3. All right, so what I've done is just copied the velocity time graph across for us. Find the greatest height that the ball reaches above the ground in the first 5.5 seconds. So you can see in the first 5.5 seconds, this should have been sort of all thought about in your reading time. So we now know after 3 seconds, it's reached the top of its upwards journey because it becomes momentarily at rest. From t equals 3 to t equals 5.5, it's traveling downwards. So really, the greatest height at reach, and because it does start at ground level, is simply, what is the area of this triangle? Okay, and of course you could have used your constant acceleration rules as well. So a deceleration of -4 and 3 for an initial velocity of for an initial velocity of 4 and an acceleration of -4 and 3. But I think the neatest way is to appreciate just the area under the curve that in that 3-second journey is equal to 6. So therefore, it's the greatest height it reaches is 6 meters above the ground. All right, find the tension in the string. So this is where it flips from kinematics to dynamics, and this is dynamics where there's only vertical motion. So you think about all those, analysis in terms of lift problems. That's the sort of thinking you've got here. So from t equals 3 to t equals 4.5, it's traveling downwards with constant acceleration. So this is the situation. So we've got our tension in the string. We know there's mg, 0.15 kilograms times g. So, and it's traveling downwards with fixed acceleration. So it gives rise to this particular equation. T, tension in the string, minus its weight force will be equal to its m, mass, times by acceleration, and it's negative because it is traveling downwards. We can add 0.515 g to both sides, and we're able to determine T to be 1.27 newtons, or you could have left your answer in terms of g, which would have been totally fine. All right, so that's it. So it's appreciating that it's like a lift problem. It's motion only in the vertical direction. So it's a bit like R minus mg equals ma analysis, the same sort of analysis you would have done in a lift problem, but it's not R in the sense of a normal reaction force of the floor onto the body as in a lift. It's R is replaced by tension in your case, but it's analysed in exactly the same way. All right, part D, find the tension in the string for this leg of the journey. So let me just highlight what we're looking at. For this leg of the journey, from 4.5 to 5.5, we notice our velocity time graph is perfectly horizontal, okay? And that's given by the two y coordinates of the endpoints there. So it's perfectly horizontal, which means it's got zero acceleration, which means it's traveling with constant velocity. And so our weight forces, it's a situation of equilibrium. Now, just going back up to this situation over here, our tension force is perfectly balanced by our weight force. It's equilibrium. It's non-static equilibrium, but it is nevertheless equilibrium because of the situation of constant velocity. So that was Newton's first law in play. All right, you can see from the velocity time graph after t equals 5.5 to 8.5, it appears to have a parabolic form to it. And in fact, that is indeed the case because here's the rule for velocity versus time. It's given by that parabola with a turning point at 5.5 comma minus 2. Explain why the closest the ball gets to the ground occurs when t is equal to 7. Well, as discussed earlier, for t in the first 3 seconds, it's traveling upwards. In the next 2.5 seconds, it's it's traveling downwards, and then it encounters its velocity being dictated by this rule from t greater than 5.5. And so whenever that rule, when the parabola hits the t-axis or the x-axis, that's representing when it's momentarily at rest, and it also signifies the end of its downwards journey. So that's what I've got here. So when graph is below the t-axis, the ball is moving downwards, and of course it's moving from a height of 6 meters. So when the graph crosses the t-axis after t equals 5.5, it transitions from downwards to upwards motion. So really, and by the way, I was extremely lenient in answering this question because it was a little bit perhaps unclear as to what exactly I was after, but I was after that sort of thinking. Any kind of solution to that equation gives rise to the value of t for which the ball is closest to the ground. So setting that equals to 0 and solving gives us a value of t equals 7 in terms of a positive value anyway. All right, the next part was certainly a little bit more challenging. Show that the ball is half a meter from the ground when t equals 7. So we know it starts from ground, reaches the maximum height of 6, and then it starts to descend. So show that it descends no more than 5.5 meters, in other words. So let's have a look. This is what I was after in this particular question. So the first part of just clearly being a continuation of the constant acceleration of -4 on 3, plus the constant acceleration thereafter. It was easily determined using analyzers of trapezium. So that area below the curve is, of course, can be just calculated nicely as a trapezium. Turns out to traveled 3.5 or 7 on 2 meters in that downwards direction. So now that we know that it's crossing the t-axis at t equals 7, we need to work out the net signed area, or work out the area of that curve, between that curve and the t-axis from t equals 5.5 to 7. Now, if you notice, I've written plus because I know because that curve is below the x-axis, it'll give me a negative signed area, which is what I want in this particular calculation. So 6 minus 3.5 minus 2, as 2 turns out to be the answer to this definite integral. And I was really looking for that definite integral in order to give you a method mark. I was looking for a second method mark being a linking of those 3 terms. So 6 upwards, 3.5 downwards, followed by a further 2 downwards before it becomes momentarily at rest and begins its upward journey, gives you a final value of 1/2. So the closest the ball gets to the ground is 1/2 of a meter. All right, so this is a nice little question. Find the tension in the string. So of course, let's just redraw the situation. So we've got tension in the string, we've got our ball, so we've got our weight force 0.15 G, our tension in the string. So tension minus 0.15 G is equal to our mass times acceleration. Okay, but what's the acceleration in this particular case? Once it's hit t equals 7 to t equals 8.5, over that 1.5 seconds, it's now traveling upwards. So acceleration in this particular instance is not constant, but is in fact variable acceleration. How do I arrive at a rule for the variable acceleration? Well, we've got a rule for our velocity. I just simply need to differentiate that with respect to t, and I get this neat little expression, 8 on 9 times 2t minus 11, and I just need to replace that in this particular acceleration. So tension in the rope minus the weight force equals mass, 0.15 times acceleration, and in this particular case, acceleration is changing as a function of time, and we've determined what that rule is. There it is, and in fact, some of you actually wrote it in a much simpler form, but I was looking for any correct expression for tension. So quite a few varieties. There was one quite neat one, but any variation, correct variation of that was deemed acceptable. Okay, this was the final part of that question. I think it was quite a nice little question. Forced you to think a bit about what you were doing here. So at t equals 8.5, the tension in the string causes the ball to slip out of the fitted cap. Find how many seconds it takes for the ball to hit the ground after slipping out, ignoring air resistance in your calculation. So that's kind of important because almost immediately you know your formulas for constant acceleration can be used quite nicely. All right, the first thing is we know that when it begins its upward journey, it's 0.5 meters from the ground. So the first thing is to work out how many more meters did it gain in that 1.5 seconds from t equals 7 to t equals 8.5. So that's a pretty simple matter of using the definite integral from t equals 7, the t-axis on our velocity time graph to t equals 8.5, and it turns out to be 4. So when it slips out from the ground, it's at a height of 4.5 meters above the ground. So of course, that's key in understanding and getting an appreciation of how to work out the time element. The next thing is to realize, well, it's traveling. In fact, if you look at your velocity time graph, the actual y coordinate or the velocity associated with a t value of 8.5 was given to you, so there was no need to work it out. It was given as 6 meters. So it's traveling at 6 meters per second upwards. So, so we know our u turns out to be 6 upwards. The total distance it travels is 4.5, but because what we're going to do, we're going to stick with the convention of positive upwards, downwards, negative. It's got to travel 4.5 meters downwards. We know acceleration is equal to 9.8 meters per second squared in the downwards direction, so minus g. And what do we need to work out? We need to work out our time. All right, so what's our go-to expression for constant acceleration? S equals ut plus half at squared. Whack that into our calculator, and it spits out 1.75 seconds. So it's the positive answer anyway. All right, good. Hopefully that makes sense. This was a bit of a challenge. There was quite a few steps involved, but hopefully it's clear enough how to get an answer. All right, welcome to the dreaded ninja question. I am so sorry to have caused people grief or to have created a negative association with this wonderful event that is the Australian Ninja Warrior. But I did watch it and I did get inspired by this question. So let me help you go through it. I think the main part of this that was difficult was there was so much information there. And in fact, that's not typical of what you can expect on the exam. There's typically a lot less literacy demand in a special paper than there is in some other areas of maths. But let's have a look at this. Okay, lot to learn from it regardless. Okay, in 2019 version of Australian Ninja Warrior, the butterfly wall appeared as a leg in one of the episodes. This leg consists of a leap by a trampoline onto the butterfly wall. Hey, so there's glance down at the diagram, trampoline, okay, righto. A 90-degree, it was 450 to match what actually happens, but that's fine. A 90-degree rotation of the wall via a central axis of rotation where the contestant moves him or herself to the outer edge of the wall. Part 3, there's a leap from the outer edge of the wall onto a hanging rope, and then there's a leap from the swinging rope onto a platform above the water. D. Now, Reshma is our ultimate ninja warrior here. Okay, so there's a lot to take in there. This is where your reading time comes into play. I'm going to break it down into chunks, what to read. The question parts below concern only steps A and C of the event. So that's what you should be doing. You should be therefore appreciating it's only these two legs that's all the questions concern. So just have a look at it and try to get a feel for what's going on here. Now, to transition between A and C was this extra step, and some of you, I'm sure, were a bit confused by that. Okay, and I'll come back to that later. Now, let's keep reading. For all parts, you may assume that air resistance is negligible. That is, acceleration is due to gravity only. Okay. When you read that, okay, what you're doing is is appreciating this can be done either with your constant acceleration formulas or with your understanding of acceleration is the double derivative of your position vector function is minus 9.8 j. All right, so that's what it means. Acceleration is due to gravity only. A lot of you really had no idea how to start. In fact, I had a lot of blanks for this question here. Acceleration is, and that's it. All right, once you appreciate that, in hindsight, this should have been part A is express r double dot t. So obviously the vector, the acceleration vector function, and it's simply that. Acceleration is due to gravity, and gravity moves in the vertical direction only. Okay, in addition, assume that all constants keep their, okay, so that's just something to try to keep it realistic. Okay, all right, let me just get rid of that. Okay, so let our position vector function be some function of ti plus some function of tj, x and y is conventional, be the position vector defining the trajectory of a point P at the base of Reshman's feet through the air. Okay, so there you can see it. This is position vector function that we need to capture. So for part A, until Reshma hits the butterfly wall. Our origin is initially set at the surface of the water, where our initial position is 2j. So you can see it's all making sense here. 2 meters above the origin, where we're starting, so origin is at water level. There we go, and x describes horizontal displacement, the x direction, and that's the y direction. There we go, bit wobbly, but you get the idea. Okay, so there's a lot to read, a lot to take in there, but that's how you just chunk it out. As I said, it's unlikely that you'll get as much reading as this in your final exam, but this is how you would do it if you did have a lot to read. Okay, so we're told A. So this was done really. Some of you, those of you who attempted it, smashed it generally. Some of you just didn't know what to do to start. And this is really the key to make a start with this problem. Okay, it's projectile motion. That's the key. Once you've ascertained it's projectile motion, air resistance not at play, that's the only form of acceleration. You start with an acceleration vector function, or you analyze it using your constant acceleration rules. Either way, it's all good. So if it takes Reshma half a second to reach the butterfly wall, and after half a second, her distance from her position from the origin is marked as 3 meters to the right and 3 meters up, 3i plus j. State the initial velocity of p in the form of r dot ai plus bj. So we're not asked to state the initial velocity. We're not asked to state the angle of projection. It's just stated as a component of I and a component of j. That's what it was about. So once you realize you start here, I think it really becomes a straightforward matter of anti-diffing. So, I mean, we can talk about the constant acceleration approach. All right, so if I anti-diff it, of course, I'm dealing with the velocity vector function, r dot of t. So, of course, it has this initial velocity in the I direction, initial velocity in the j direction, and there's the anti-drift minus gtj. I anti-diff it a second time, and I'm left with this particular expression. The only difference between the I and the j components is the 2 gets absorbed in the j component because, of course, R0, the initial position, is equal to 2j. I need to factor that in there. All right, that's it. So once I've established this, it really becomes quite easy at linking that with the required information and solving for A and B. So replacing t equals 1/2 in the rule. Okay, so r of t could be described as r of 1/2. So the position vector function when t equals 1/2 is a 1/2 times a, or a on 2i, plus 2 plus b on 2 minus 4.9 times 1/2 squared is equal to that. And then it's a case of, well, if we know that that's going to be equal to 3i plus 3j, we can equate parts, and we're left with these simple equations. So equating the I components we can quickly determine that A is equal to 6, equating the J components, 31 and 40 equals plus B on 2 equals 3, leads us to B equals 89 on 20 or 4.45, and we can express our initial velocity in terms of its I and J components quite neatly. All right, I think, again, if I was to have my time over, the beauty of hindsight, part A would have been to state R double dot of T, and it would be simply that, and hopefully that would have sparked you to follow the right path. Now, of course, you could have analysed it. It's travelling with constant velocity in the x direction. So it's actually in the x direction. In the x direction, it's travelled 3 meters in half a second. And in the y direction, because we started at 2J, at 2 meters above the water level, and we finished at 3 meters, it's gained 1 meter in half a second, and working with a acceleration of minus g, so you could have actually worked it out quite nicely with your constant acceleration formulas as well. All right, then there was a bit to interpret. There was because this is a 3D situation, this is what's actually happening. Hopefully, my diagrams were there to help, but it was complex information indeed to interpret. So here is the direction of the trampoline. There's the direction of the hanging rope. There's the positive x direction. Now the butterfly wall lies flush to the receiving Reshma, who jumps from the direction of the trampoline. She lands on the butterfly wall, and then the wall undergoes a 90-degree rotation until it aligns with the y and x direction, as we'll see. Here it is. So the wall rotates, and then the edge of the wall aligns with the x-axis again. This other axis, a student asked me, what is this other axis? Of course, that would be the z-axis if you really had to put a label to it. It runs perpendicular to the x and y plane, okay, through the origin. But there it is. So the butterfly wall spins around, and then it enables Reshma to jump off from the edge of the butterfly wall, who's hanging on for dear life over here. There's where her hands would be, and there's her feet. She leaves it at point 2, and then we'll talk about how she leaves it shortly. But that's the situation. Now, to understand that, I guess you had to really go back to, and this is the complexity of the information as it's set out. We've completed part A of the journey. Reshma is now on the butterfly wall. It's undergone that 90-degree rotation, and the edge of the butterfly wall is now aligned with the XY axis. Now, what we do have is a new origin. So the origin is now at the center of the butterfly wall, as you can see in this diagram here. So the very center lies, and that's XY is this axis of rotation. So it's undergone that 90-degree rotation, enabling Reshma to jump off from this point to the hanging wall. So there was a lot to take in there, and as I said, I think the literacy demand in a special exam is usually much less than that. So, but that's what was going on. Please ask me to clarify for you later if you're still not sure of what's actually happening in this scenario. Okay, so I've just compacted it a little bit. Sorry if it's a bit hard to read, but here's the, now with the origin at the center of the butterfly wall, this outer edge of the butterfly wall actually takes the form of a hyperbola. Now, I had a lot of fun coming up with the rule. That was the best equation that matched the approximate dimensions of the outer edge of the butterfly wall. And it's nice that it's an equation recognizable by you as one of the types of graphs you need to be familiar with. Okay, so there it is. So here's the hanging rope. It's basically it's a straight line, vertical straight line, has the equation x equals 3. So Reshma leaps off the wall in a direction perpendicular to the slope of the gradient of the outer wall at that point P2 there. So here's the point P2. If I was to draw a tangent P2, it would look like this, and show she's leaping off in that's her initial direction that she leaps off. So running perpendicular to the gradient of the slope. So that's what's going on here. So show that the angle that this direction makes with the horizontal is 12.6 degrees. So basically, let's think about how do I work out, given a graph on the XY plane, how do I work out angles straight lines make with the horizontal? It's all about, this is where your thinking goes, m and theta. So theta equals inverse tan of m. So what I need to do is firstly work out the gradient of my curve at that particular point, at point M1, at point P2 rather, and of course here's gradient of my the direction that Reshma takes off in, and that'll be the negative reciprocal M1 because it runs perpendicular to the slope of the gradient. So okay, so with linking all of that together, it's all about, well, what's the general rule for the gradient of that hyperbola? You could do it by hand or use your imp-diff feature of your CAS calculator. Okay, so I've just done it by hand, but of course there's no need to when you've got imp-diff in your calculator, but it's of course a relation involving x and y, so it's that's what you'd need to do to differentiate it. So differentiating, I've got a rule for dy dx is 4x divided by y. Go through the understandings for yourselves. It's very doable by hand. Okay, so what's the gradient of the hyperbola at that particular point? 2 root 5. Clear off some of that. That's the point there. 2 root 5 on 5. 4 minus 4 on 5. So that's the point. So what's the slope at that particular point? It turns out to be minus 2 root 5, and you can see that makes sense just looking at the picture. So it's got a negative slope to it. It's reasonably steep. So what's the gradient of the line in which Reshma takes off from P2 at? It's going to be the negative reciprocal of that. Turns out to be 1 divided by 2 root 5, and I just take the inverse tan of that gradient value. That should be 12.6, pretty damn close to 12.6 degrees, so, which is always comforting. All right, that was done not too bad, but yeah, it should have been really stemming from your understanding of what's required, understanding it's an m equals tan theta relationship, and therefore working with gradient. Okay, here we are. So the rope hangs 3 meters from the central axis of the butterfly wall. There's the diagram supplied for you. Let V be Reshma's initial speed projected from the butterfly wall, and T be the time Reshma is in the air before reaching the rope. So this is her initial speed, and T is the time that it takes to reach the rope after leaving P2. And there's the coordinates of P2. So you may assume her trajectory can be modelled in the x and y directions only. So there's no sideways movements, in other words, as she's jumping from the edge of the butterfly wall onto the hanging rope. If Reshma reaches the rope at maximum height, so here's what I've done is I've actually got a dotted line for her trajectory. You can see it's going to be the parabolic in shape, but I've tried to draw it in such a way to indicate that if she was to continue, it would be continuation of that parabola, but she's reaching her maximum height when she hits that hanging rope, hanging 3 meters from the central axis of the butterfly wall, in other words, with an equation of x equals 3. All right, so B is her initial speed, T is the time. State two equations involving V and T that model this situation. All right, now the first one is the more straightforward of the two, and that's simply, what is the horizontal distance that she has to cover? Is this, and of course that's an x value of 3 from a starting x value of 2 root 5 on 5, and that's the horizontal she covers in a time of t. So it's 3 minus 2 root 5 on 5. So V cos 12.6, so that's her initial velocity resolved in the I direction times by T, it's constant velocity, and that's what I was looking for as an answer, one of the two equations to give. Okay, moving on. This was perhaps the harder component. The vertical distance, of course, occurs when, so what I've done is just analyze it using constant acceleration understanding. So constant acceleration resolved in the J direction. So her initial velocity is V sine 12.6 degrees. We need to find out the distance she covers when the final velocity is equal to 0. So V, so it's perfectly modeled by constant acceleration rules. V final velocity 0, U is of course V sine 12.6. Acceleration is just simply G working downwards in the minus direction times by T, and that's the sort of equation I was looking to find to model the changes in the vertical. Okay, now an alternative way to go would be to just set up, again, start with R double dot T equals minus G in the J direction, get an expression for R dot T, and appreciate that's going to be equal to, V cos 12.6 degrees I plus V sine 12.6 minus GTJ, and setting the J component to 0. So we could always set the J component to 0 in our R dot T in our velocity vector function and arrive at the same rule. Okay, so hopefully that's clear enough. All right, here's the final part of question 4. It couldn't come fast enough for many of you. But yeah, okay, let's have a look at it. So Reshma successfully completes the leg. So this is just story. The next contestant, Rahul, however, had too much downward momentum to hang onto the rope and fell into the water. He too launched from the same point, which is given to you again, 2 root 5 on 5, comma, minus 4 on 5, at the same angle to the horizontal of 12.6. However, his initial speed was just 7.2 meters per second. Okay, let the trajectory of Rahul through the air also be modeled relative to a point P beginning at P2. Find the acute angle that the trajectory of point P makes with the vertically hanging rope, given that it took point P 0.3 seconds to reach the rope. All right, so we're told his initial speed. So initial speed was 7.2 meters per second. Okay, we're told that the angle of projection was 12.6 degrees, same as it was for Reshma. And we're told that the time it took him to reach the rope was 0.3 seconds. Okay, so we've got enough information there without having to do too much in-depth mathematics to work out the angle at which Rahul will be, well, the point P at the base of Rahul will be intersecting with the vertically hanging rope at x equals 3. How do we come by that information? Well, of course, it's the velocity vector function that drives direction. So it's the R dot T Rahul is what we just need to bring up. So I guess you've got a mark for that, appreciating we're dealing with the velocity vector function. Or of course, this could be done again with constant acceleration rules, but let's just go through this for now. So in Rahul's particular situation, there it is, that's his constant velocity, 7.2 meters per second resolved in the I direction, cos 12.6 plus 7.2 sine 12.6 minus GTJ. Now we're told, I didn't have to give you that information, but it was just to save some time. We're told that T is equal to 0.3 seconds in this particular case. And then we've got both the I and J components for his velocity at the moment Rahul hits the rope. So here it is. So you can see this equation over here models what's going on here. So it's 7.2 12 plus 12.6 is the component of velocity vector at 0.3, and then I replace t with 0.3. The magnitude of that gives us our downwards. So if you actually did 7.2 sine 12.6 minus 0.3 times 9.8, you'd see it have a negative component to it. We know that the j component is negative because we're talking about too much downwards momentum. So we know that that j component would have to be negative, but you can just, the maths would do it for you. Turns out to have a negative value. So here's your I component of the velocity vector at 0.3. Here's the j component. And of course, here's the angle it's making with the vertical, which is the angle it's making with the rope. So unlike some other questions you may have done in the past with projectile motion, the angle which it's hitting the sea, for instance, with a cannon launch or something like this. This is, and of course it was your j component divided by your I component, magnitude of your j component divided by your I component, inverse tan. But this is of course the I component divided by your j component because it's the angle it's making with the vertical, not the horizontal. So that's what we do, and there was your answer when you did inverse tan, and a few of you got that right, which was pleasing. All right, this marathon vodcast is coming to a close shortly. We're on to the final extended response question. Nossal Private Hospital is the latest hospital to operate in the city of Casey. In the first month of operation, our nurses promptly responded to patient calls for help. The probability distribution for the random variable x representing response times in minutes, can be modeled by the following probability density function. There it is. Okay, find the expected value and the standard deviation. I later made it show that the standard deviation was equal to a particular value, but that's all you needed to do to find the expected value. Of course, you should know that. It's just taking your density function, multiplying it by x, and of course it's only in play from x equals 0 to positive infinity. You just whack that into your calculator. It should have been easy enough to show that the expected value was 1 minute response time. That's pretty good. Okay, show that the standard deviation of response times was equal to root 3 on 3. So of course, I was looking for the right methodology. Expected value of the random variable x squared minus the expected value of x squared, the square root, and that led you to the correct answer. That was done well, and if you're having trouble with that, please, that's methods 101 sort of stuff, so make sure you're good with your understanding. Okay, C, find the probability that a random sample of 48 patient calls for help. Nurses at Nossal Hospital responded on average within 55 seconds. Okay, firstly, different units, seconds versus minutes. So understand that we're dealing with 55 on 60 minutes. But of course, this is the central limit theorem. That's what this is all about, central limit theorem. Despite the fact that x was not a normal, was not normally distribution, we take a large enough sample size, which 48 clearly is. If we talk about the sampling distribution x bar will be approximately normal. Okay, so the mean and that normal distribution will be equal to the mean of x. So we know part of the central limit theorem, that's equal to 1 that we've calculated before, and the standard deviation of x bar is equal to the standard deviation of x, which is root 3 on 3, divided by the square root of the sample size, turns out to be 1/12. Okay, so the probability that x bar will be less than 55 on 60, or 11/12 of a minute, is in fact equal to 1 standard deviation below the mean, and it turns out to be 0.1587. Okay, so that was done okay, and that was your test of the central limit theorem. Okay, this part was my error on the, the question was fine, but it was It was a ridiculous answer. Nevertheless, it was a perfectly valid question to ask, so there was no need to adjust marks for it. Probably would have made you second guessing yourself, and I'm sorry for that. I'll talk about what I did wrong in a second. Okay, at another hospital, McRobertson's Hospital, the mean response time was 3 minutes. Now, that should have been much closer to 1 minute to make this a decent question, maybe 1.2 minutes or something like that, with a standard deviation of root 3 on 2 minutes. So greater variability because the other one was root 3 on 3, and certainly a much greater response time. In hindsight, that should have been much smaller. Anyway, doesn't matter. So that's McRobertson Hospital, Nossal, McRob. Okay, anyway, doesn't matter. That was the intended playoff. D, find the probability that the mean response time from a random sample of 48 calls for help from patients at McRob Hospital will be faster. Okay, firstly, their response time's shorter. So sometimes faster you think better, so larger, but in case this is response times smaller than that from the similar random sample of 48 calls from patients at Nossal High. So 48 calls, obviously, so you didn't have to do any major recalculations. So find the probability that a sample estimate of 48 of response times from McRob will be less than the sample estimate of 48 with the sample size of 48 of patients from Nossal High. So this is what we're after. So first thing is we need to work out, understand that in the sampling distribution for response times in McRobertson's High, it shares the same mean that it's of 3. So, but of course, the standard deviation is not root 3 on 2, but it's root 3 on 2 divided by the square root of 48. It turns out to be 1/8. So here it is. So y bar is approximately normal. That's what that notation is quite neatly capturing, with a mean of 3 and a variance of 1/8 squared. Okay, let's move on. Okay, so what we're doing is talking about two normal distributions, x bar, the sampling distribution of 48 from Nossal, and y bar, the sampling distribution of 48, sample size of 48 from McRobertson's. Okay, so this is the intention was you set up T, so let T be a member from X bar minus a member from Y bar. So we know T will also be normally distributed because X bar and Y bar are also normally distributed. Okay, so what we want to do is find the probability that T is positive. In other words, that that Nossal response time will be greater than McRobertson's response time. Now, because I set the mean to be so high, it became impossible, as we'll see. But anyway, this is what I was looking for. So the expected value of T is obviously expected value of X minus expected value of Y. Turns out to be -2. And of course, you could have set it up in the opposite way. The variance of T was the variance of X bar plus the variance of Y bar. Why plus the variance? Because the multiple of the is -1, so we could think of it as we could think of it as T as being X bar plus -1 times Y bar. So it fits nicely the rule. So it's a sum of two normal random variables, and of course we take the multiple and square it, which is what I'm doing over here. Obviously, -1 squared is +1, so we just need to sum the two variances. What I forgot to do, of course, was I forgot to divide by the square root of 48 in both, and I got an answer that was much nicer, but that was my bad. Anyway, it was still a valid question, as I said. So here's the variance of X bar was 1/12 squared plus the variance, the standard deviation of X bar was 1/12. So there's 1/12 squared plus the standard deviation of Y bar, which is 1/8. So plus 1/8 squared leads to this value. What do you do then? You work out the standard deviation of T by taking the square root of that. Turns out the square root of 13 on 24. And to work out the probability that T is positive, it was impossible. because y bar, because the expected value of y, this is really y, was 3, was so much greater than the expected response time for x, and that led to an impossible answer. So the correct answer was 0, or 0.000. It's, for the 4 decimal places. So sorry about the confusion that gave, but that was indeed the correct answer to that particular question. So it's more the process I want you to follow than anything else. So hopefully you'll ask me questions if you're unsure about that at all. Okay. At Nossal Hospital, a new dispenser of liquid medicine is intended to accurately deliver a fixed dose of medicine. Let M be the random variable for milliliters of liquid medicine dispensed. Okay, now M bar is our point estimate for the average dose. Now 100 such doses were recorded, and from this we created a 99% confidence interval, and it was calculated to be this. So greater than 2.43909 and less than 2.50091. Show via a pair, so via 2 appropriate equations, that the sample estimate was indeed 2.47 mils, and the population standard deviation that we used in the calculation of this 99% confidence interval was 0.12 mils. Okay, so really what was I after? I was after an equation to appreciate that the average of the 2 endpoints of the confidence interval gives us our sample estimate of 2.47. So I was looking for an equation to mark for something of that general nature. And I think that was done reasonably well. What about the confidence interval? Now, what I did was I just appealed to the margin of error. So the margin of error, the difference between 2.47 and one of the endpoints, equals the K value marking a 99% confidence interval times by sigma divided by the square root of the number of samples divided by the square root of 100. But what was that K value that marks a 99%? I wanted you to be able to work that out with your calculators. And of course, 99% of the population in a normal distribution, when reduced to a standard normal distribution, turns out to be between minus 2.5758 and positive 2.578. So how do you make that determination? Of course, just your inverse norm. You could set your inverse norm to left tail, left tail, and obviously equals to half of 1%, so 0.5%, or of course 0.005 would mark half a percent. So you use your inverse norm to work out what the Z score would be. So it turns out to be 2.5758 standard deviations. Anything more than 2.5758 takes you beyond beyond the 99% central, beyond 99% of the common doses that you will receive. So that's it. Okay. So anyway, so margin of error, it's that factor 2.5758 times by the standard deviation of our population divided by the square root of the sample size, which equals the square root of 100. And that margin of error is the difference between our center of our confidence interval, which was our M bar value, and an endpoint. And that's the equation I was looking for in being able to identify what the standard deviation that they used in this particular calculation. Hopefully, my rambling made sense to you. It's the end of a long podcast. I think you appreciate that. All right, we're on the home stretch. The dispenser is intended to dispense precisely 2.5 mils of liquid medicine with a standard deviation of 0.12 mils. A nurse suspected the dispenser was malfunctioning. What does that mean? That means dispensing with a mean other than 2.5 mils. other than non-directional. Okay, and most of you got this correct, which was nice. Accordingly, he tested his hypothesis against the above-mentioned point estimate of 2.47, 1% level of statistical significance. So in other words, alpha is equal to 0.1. So it's obviously it's matching the confidence interval information given above, and that's what I was hoping you would be able to link in the next question. Nevertheless, let's have a look at F. State the null and alternate hypothesis proposed by the nurse. Most of you did this correct. Most of you were onto the fact that it was a non-directional alternate hypothesis. So mu is equal to 2.5, dispensing what it should, and alternate mu is not equal to 2.5, dispensing something other than what it should. Okay. All right. State whether the nurse should reject or not reject the null. Now, simply this. The 99% confidence that was given to you in the question was from 2.43 something or other up to 2.53 something or other. It contained the intended, it contained the amount intended to be dispensed. So because that 99% confidence interval contained the amount, contained the null hypothesis mean amount, it means that the nurse should not reject the null hypothesis, and we're able to reach that conclusion without going to the trouble of actually calculating the p-value. All right, so that was the intention of that. Now, if you went on and calculated the p-value and arrived at the same conclusion, of course, you got that mark, but indeed, you lost time in being able to, in going to your calculators and creating that p-value. So that piece of knowledge would have assisted you with your time management in this particular question. Okay, moving on. Express your answer to, well, it should have been part G, so the part above, using a notationally valid probability expression for the p-value and an inequality involving alpha. Look, at the end of the day, I accepted. A lot of you did the notationally valid expression for the p-value, but forgot about the inequality. I just marked the probability statement in its own right. So here are three different ways that I would have accepted. So it's obviously 2 times the probability that the sampling distribution is less than the sample estimate, the point estimate, given a center of 2.5. So that sort of notation would have given you 1 mark. Another way to do it would have been to say the probability that a member of the sampling distribution, its distance from the center of 2.5 is greater than 0.3. So again, stating given that the center is equal to 2.5. And here is the third way, of course, is going at the top end. So given that the 2 times the probability, okay, so it's linked to that first option. So rather than saying that X bar is less than 2.47, you're going X bar is greater than 2.53. So the same distance it is from the center, but looking at the top end of the tail and multiplying that top end of the tail by 2. So this is the bottom end of the tail, which is the more sort of sensible way to express it, given that our point estimate was below the mean. Nevertheless, you could have equally expressed it using the symmetry of the normal distribution as 2 times the top tail, or you could have just used this notation of distance of the sample estimate being greater than 0.03. And of course, this is the other bit of information that I wanted to see, but some of you failed to do that, and in the end, I decided to turn a blind eye to it. I was hoping that that expression for probability greater than alpha to indicate that there was not enough evidence to reject the null. But anyway, that's I was a bit flexible with that particular element of the question. Okay, and finally, I thought a lot of you would do better on this question because we did practice it a few times in class. Okay, let's go through it. It turns out that the device actually, so there's that keyword, actually dispenses. This is the idea that, not that we could ever know this, but in the mind of the all-knower, this is actually what's going on. The device actually dispenses liquid medicine with a mean of 2.48 mils, but with the same standard deviation of 0.12 mils. State the probability that the nurse will make a type 2 error. So what is that all about? That they'll think that there's not enough evidence to reject the null. In other words, the p-value is greater than alpha. But in fact, so they've gone through the process, the p-value is great, but in fact, they should have. Okay. Now, in fact, they should have, of course, they should, in this particular scenario, reject the null because in fact it's not true. Not that they would know it as testers, but it's in fact not true that the dispenser is dispensing liquid medicine with a mean of 2.5 mils precisely. It's in fact doing it with a mean of 2.48 mils. So provided that the nurse doesn't reject the null, the nurse is making a type 2 error. So that's just based on the fact, the actual information given to us in the question. All right, so what am I doing? I'm just setting up some notation to make it clear how to set out some working out. So I'm calling x star the actual random variable, x being the supposed random variable for the amount dispensed by the dispenser. So okay, so we know that the standard deviation in a sample of size of 100 is the standard deviation of 0.12 divided by the square root of 100, so it's 0.012, and that's something shared by both the actual standard deviation of the sampling mean and the supposed sampling standard deviation of the sampling mean. Okay, so let's go to our x bar, the supposed. So we're working with the supposition that it has a center of 2.5, and with the standard deviation of 0.12, but 0.12 divided by the square root of 100 gives us the sampling distribution of x, and this is what we're working with. So we're working with the understanding that it falls with these under these parameters. So here it is, our center of 2.5. What I need to do is use our inverse norm to work out what it would be at the bottom 0.5% and what it would be at the top 0.5% under this normal distribution with a standard deviation of 0.012. And that's easy enough to calculate as 2.469 and 2.531 using our inverse norm. Bottom, so left tail 0.5%, right tail 0.5%. I'm able to get those two values. We'll make it a center of 0.99%, and you'll be able to get the left one, and then you can adjust that left one for the right one. It's the same distance from the mean or the center of 2.5. All right, so let's understand what we've just calculated here. So for the nurse, they've gone and created another point estimate. That point estimate turns out to be between those two values. If that's the case, the nurse will naturally feel that he doesn't have enough evidence to reject the null hypothesis using a 1% level of statistical significance. Hopefully that's clear enough. So using a 1% level of statistical significance, any point estimate between 2.469 and 2.531 will lead that nurse to not rejecting the null hypothesis. Will have a p-value greater than 1% in this two-tailed test environment. Okay, all right, good. So continuing to move on. Okay, so what percentage of area under the actual distribution do those two, between those two values, does that represent? So this is where we go to x star bar, so the sampling distribution for the actual liquid dispensed from this device, and what we're doing is just using our norm CDF now. So the probability that x bar star will be greater than 2.46 and less than 2.51 turns out to be 81.84%, and that's just straight up using your norm CDF. So that's a question. Perhaps the wording intruded on some people's thinking, but it's a question that we had practiced fairly well several times in class, and hopefully you would have practiced as part of your revision. So be on the lookout for that. Those type 2 error questions always follows the same process of reaching a solution. So hopefully this in-depth look at SAC 2 will be of use to you, and hopefully the sort of questions you've encountered will you'll no longer have issues with as you're going on towards your trial exams and the big one in November. So that's it for me. It's been a bit of a marathon. We'll talk soon. Okay, bye.